Welcome back. Today we'll be talking about data problems, specifically problems that can bias the mean and/or the standard error of a distribution. Before we get started, it's important to place this topic in the larger scope of measurement. Hopefully you're already comfortable considering questions about the reliability, that is the consistency between measurements, and the validity, the accurate and complete representation of a concept of interest in relation to instrument design. Such problems, particularly in design and collection, can, at best, attenuate or shrink our estimates of real effects, and at worst render data basically unusable, or even lead researchers to make the opposite conclusion of what they should. So we can't ignore the validity or reliability of our data collection. Likewise, there could be outright errors in data where responses are given codes that aren't valid, that one's fixable, or just misrecorded. For example, someone accidentally clicks the wrong box on an internet survey, which is much more difficult. These are both problems of bad data. Today, though, we're talking about a different and often more insidious kind of data problem, when good data go bad. In real life, many variables are not normally distributed. For example, income has a right skew, or a positive skew, due to a small number of people with very high incomes. Lifetime years of paid employment, which is used to help calculate Social Security eligibility, is bimodal. Many people work nearly their entire adult life until retiring in their 60s or 70s, but a large number also work for only a very short time, if any at all, because their partner is able to fully support them. The important difference from before is that these data are right. They accurately represent the population, or at least members of the population, but as we already saw for the mean, outliers and non-normal distributions can severely affect estimates, even when they're true. Specifically, the value of a single outlier has a linear effect on the mean. That is, for every unit it is above or below the rest of the distribution, the mean increases or decreases by a factor of 1 over n. So if 10 people have incomes of $10,000, $20,000, $30,000, and so on to $100,000, the sample mean is $55,000. For every $100,000 higher that top value is, the mean of the entire sample increases by $10,000. So if that person earns $600,000, for example, the mean would be $105,000, more than double the mean if you left that one case out. And the mean would be above the highest value in the original distribution. In statistical terms, outliers bias the mean to be unreflective of the shape of the overall distribution. If you were to superimpose a normal curve on a histogram of income, its peak, the mean, would be well to the right of the actual peak of the distribution. Variance, and also then standard deviation and standard error, are even more dramatically affected by outliers, though, and particularly because they use squared errors for extreme outliers, although there's no simple equation for the effect like the mean had. And while the mean is biased toward the outlier, up or down, so we can kind of tell the direction it's going to be if we know our data well, the standard error is always biased upward. So for our income distribution, the increase in variance due to outliers would stretch out the curve, making it platykurtotic and widening the confidence interval of any estimates dramatically. Which brings us to the crux of our problem. Unlike when we were just trying to summarize our sample and could choose to use the mean, the median, or the mode, there's no single agreed-on way to substitute another statistic for the mean or the standard error in inferential statistics, like confidence intervals. The widened confidence intervals will increase the probability of type 2 error. That is, the wider range of possible samples leads us to ignore effects that actually do exist in the population. For the mean, the problem can be even worse because a biased mean doesn't necessarily make us more conservative. Instead, it can cause us to miss true effects. By pulling the mean away, it can also, though, lead to us to conclude that there are effects, when really it's an artifact of sampling error, and either there are really no effects, or worse, it's the opposite of what you thought, and the opposite of what your data says. There are also ways the standard error can be biased downward. So imagine we wanted to study the color of M&Ms in packs. We bought 50 packs, poured them all into a bowl, and measured the proportion of each color in the bowl, coming to what we assume is a representative distribution of color counts, right? But what if, instead of normal packs, standard packs of M&Ms, each of the 50 packs was actually only a single color? By pouring them together, counting them all, and then dividing by the number of packs, we get a plausible mean and standard deviation, when in fact there were a number of different types of packs, or a number of different populations, with very different characteristics that just happened to look fairly normal when mixed. So are we stuck with all these problems and we just have to deal with unrepresentative or deceptive results? Not by a long shot. Much of the last 80 years has been spent developing ways to deal with more kinds of non-normality than any one person can think of, and luckily some of them are relatively simple. But that's a story for next time. Thanks for watching. Have a great day.